I am a bit late. I didn't want to call you back because I think you were enjoying a lot the sun outside. I will keep lecturing up to 1:30, 1:35. Okay, so this sketch basically reports what I already mentioned to you. So the interplay between fresh water and groundwater. The sketch on the screen looks less clear, but if you look on the website, I think it is clearer. Basically, it is a section of an inslope with also a third dimension. So what you see, I hope that you can see the mouse. Let me see. Yeah. This is the sea, and this is the sea in depth. This is the sea in the space, in the two-dimensional space of the Earth's surface, and this is sea depth. Here you have the saltwater wedge. So from the sea, this is the sea bottom. You see that sea floor. Yeah, I couldn't read here. This is the sea floor, and this is the wedge of salt water entering into the land. And you see that I put the tree here with the roots very close to the freshwater saltwater interface. Keep in mind that a tree can grow up if the roots can manage to find fresh water, because the tree can't survive with salt water. And therefore, when you see trees, I think this is an interesting exercise. Sometimes you see trees on beaches, very close to the sea. And try to understand how this is possible. Usually in landwards, you have slopy hill slopes, which means that you have a flow of fresh water reaching the beach, because it's almost impossible that you find a tree in a flat beach, because there is no fresh water coming from the land. Usually when you find a tree like in this position, very close, is that because on the land side you have an inslope which brings water. And it's interesting. Try to, next time that you look on the seaside, to look at vegetation and try to understand where it is displaced. And you will notice that over the dunes, as I already mentioned, there are brushes. And if you move inland, then you start finding trees. And try to understand, because it gives to you an idea of the groundwater dynamics. Trees are excellent indicators, like wells, of groundwater dynamics. Okay, so here you have the tree, and you may have rivers coming down, and here you have a saturated zone, which is below the water table, and here you have infiltration from the mountains, reaching the groundwater body. And the groundwater body flows towards the ocean, the sea. And here you may have wells from which you pump water. So we have to understand this interplay. Also, in the land you have houses with maybe impervious areas, because urbanized areas are typically, let's say that they have a reduced permeability, and houses may take water from personal wells. So we have to understand this interplay, and first by observing. Okay, let's move forward. And in order to understand the interplay between groundwater and salt water, we need to make a brief recall of groundwater dynamics, which is basically, what is groundwater dynamics? What is groundwater? Groundwater is a water body located in the underground. Usually it's slowly moving. Usually it's not in steady state. Usually it's slowly moving. Why is that? Because it's fed by rainfall through infiltration, and therefore an extra storage is created. And when there is an extra storage, then the water in excess flows down towards the sea. And this movement typically is very slow. as compared with the water movement in rivers. Water velocity in rivers is about from 0.1 to 1 meter per second. And 1 meter per second is quite a huge velocity for water in river. Usually we range between 0.05, 0.1 meters per second. In groundwater we talk about centimeters or millimeters per second, which means a couple of order of magnitudes lower and in terms of velocity of the flow. But it's moving. And therefore, if it's moving, it means that there is energy that is spent in order to keep the water moving. And while moving, fresh water, pushes back the salt water. What is the law which describes underground water flow? It's Darcy's law. Darcy's law, there is an explanation on my web pages, there is a link to Wikipedia. Darcy's law basically describes a water flow that takes place at the pore scale. It's extremely complicated. It's a water flow that is more complicated to describe with respect to describing water flow in rivers, because a river is observable and also the control volume, the geometry, is easy to define. I mean, even if it's sometimes complicated, one thing is to describe a geometry of a river, which is, maybe complicated, but still it's quite simple. Another thing is to describe something, a water flow that occurs in pores between, that are located between grains in a porous media. So basically you have a flow that takes place along these pores. It's more complicated, of course, to describe. There is the advantage that the velocity is very low. So everything that moves slower, it's easier to describe with respect to something that moves very fast, of course. And Darcy's law, basically, is a relationship that relates the velocity of water to energy dissipation. And it's expressed here. So if we want to describe usually our problem is to describe the water flow, to estimate the water flow through a porous media. First thing, we have to identify a cross-section of this water flow. So we go into our porous media. Let's suppose that here there is the ground. And let's suppose that you have here a porous media below here, and which may be limited by a bedrock. So let's suppose that you have a water flow coming from the blackboard towards us, and let's assume that this flow is represented by a velocity vector. Actually, this velocity vector changes at the microscopic scale because water flows into the pores. So it's extremely difficult to describe in detail at the micro scale this movement. So our choice is to describe an average velocity vector averaged over an area of interest. So let's suppose that we have here a portion of aquifer that we decide to investigate because for some reasons, maybe because here we have a well, and therefore we isolate an area of the aquifer which we want to investigate, or maybe that we extend our area of interest to the whole aquifer. It's no problem. That's just to assume that we have an area of this aquifer in the 2D dimension that is given by the blackboard, which we are interested in estimating the water flowing from water that comes from this area into the room because it comes out from the blackboard. And let's assume that we can describe an average velocity vector from this area. And let me depict it in this way, like a vector that is coming out towards us. And let's assume that this area is perpendicular to the velocity vector. So basically what we do, if we look at the underground, we isolate a portion of the aquifer which we are interested in, and let's suppose that we can estimate a velocity vector, the average velocity vector of the flow into that portion of the aquifer. And now let's look at the blackboard. Let's suppose that this is our portion of aquifer we are interested in, and we basically identified this plane by cutting the aquifer with a plane that is perpendicular to the velocity vector. And therefore this vector, velocity vector, is coming out from the blackboard and it's perpendicular. Okay? We can always do that. Once that we fix a volume of the aquifer we are interested in, we can estimate a velocity vector, an average velocity vector for that volume, and that we can cut that volume with the blackboard in a way that the blackboard is perpendicular to the velocity vector. Why we do that? Because in this way we reduce the 3D problem to a 2D problem. Because basically we assume that velocity of water is along just one direction. So it's a problem that water is flowing along one direction, and we estimate, we fix the blackboard to cover the other two directions. Okay, so let's suppose that this is the velocity vector. How can we estimate the water flow? So volume of water per unit time that comes from this area by assuming that the velocity vector is perpendicularly coming out from this area. If we indicate the flow Qt with the symbol Q, depending on time, what we have to do is to multiply the velocity vector times the area of the cross section. Every time that we have a flow along one direction, if we cut the flow with a plane that is perpendicular to the velocity vector, we get a cross section. Okay, so basically, if you look at this relationship, I think you already know it. It applies to any current or flow. You take a cross section of this flow. Keep in mind that a current is defined as a water flow where the velocity is more or less the same direction for all the fluid particles. This is a current. A current is what happens in a pipe. If you have a pipe, you have several fluid particles that are moving, and their velocity vector is the same, along the same direction. It is a different situation if you take a glass of water and you put the glass upside down over a table. You have any drop of water that flows in different, the velocity of the drops of water over the table follows different direction. This is not a current. A current is a water flow where each drop is characterized by a velocity vector and the direction is the same, like in a pipe. Or like in a river. In a river you have a dominant velocity direction. Okay, perfect. Then if you have only direction for velocity, only one direction, you can cut the flow with the plane perpendicular to the velocity vector. You obtain the cross section, you indicate the cross section with A, and then if you take the velocity, which is the same for all the fluid particles, my definitions, times area of the cross-section, you get the water flow. I hope this is a brief recall, very short recall of fluid mechanics. I hope you remember it. If you don't remember it, I hope you understood it. If you didn't understand, let me know, now or next time, okay? This is essential because you have to recognize when there is a water flow, when you can assimilate it to a current. So get several drops in this flow and try to see if the velocity vector has the same direction for each of the drop. More or less, I mean, you don't need to be precise like that, but more or less the same. If the reply is yes, this is a current. Okay, so you have only one velocity direction. And then you can cut the current with a perpendicular plane to the velocity, you get the cross-section, and you estimate the flow in this way. Okay? And this is dimensionally consistent because if you look at dimensions here, water flow is defined as volume rate per unit time. So length cube divided by time. And here you have velocity, the dimension of velocity is length divided by time. And you have the area. The area is length squared. Fine. You see that it's dimensionally consistent. Okay, now our problem is to estimate the flow. We know the area of the cross-section because we define the region of the space we are interested in. It's missing the velocity. We need to estimate the velocity. So how to estimate the velocity of a groundwater flow? Then Darcy's laws comes into play. Darcy law. Basically, what it says is that the velocity Wt is given by a constant which is called hydraulic conductivity. Let me see if I can write it and then I move to let you see it. Hydraulic conductivity. Times the decline over time of over space, sorry. Of hydraulic head. And then I'm explaining to you now what's hydraulic head. Hydraulic conductivity, as I said, it's a constant. It's an hydraulic property of the medium, and it has a dimension of a velocity, because the decline over time of the hydraulic head is adimensional. And now I have to explain what is hydraulic head. First, what is the head? The head is a measure of energy. It's a measure of the energy of the flow. And therefore here you have a decline in energy. Basically, what does this equation say? It says that velocity is directly proportional to energy decline, which is reasonable. If you think about motion in general, it's perfectly sound that you affirm that the velocity of the motion is related to decline of energy. Perfectly sound. But you should also remember that in some cases, in your previous studies, you learned that energy dissipation for moving a body is proportional to the square of the velocity, not linearly proportional to the velocity. I'm sure that you remember that. You studied in several cases, for instance, that the resistance that is offered by air to the movement of a car is proportional to the square of the velocity. So you should now wonder why, in this case, energy decline, which is equivalent to resistance, it's linearly proportional to velocity. And the reason is that the flow in the groundwater is extremely slow, I was saying, is extremely slow. So the fact that the slowness, the fact that the flow is slow, it's not fast, allows us to assume this linear relationship between energy dissipation and velocity. This was the finding by Darcy. When he proposed this law, he was aware of the fact that in general for a body, for a moving body, energy dissipation is proportional to the square of velocity. And how did he find it? It's very simple. He did what any scientist usually does. He made an experiment. If you look at here, what he did is exactly what you can see. Basically, he put some sand into a tube, a vertical tube. Indeed, his tube was not vertical, it was horizontal, but it doesn't matter. He put sand, so basically where you see A, the symbol A, you see a white region into the tube that is comprised between the light blue regions. White means sand. He put water on the top of the tube, and he measured the energy of water, the hydraulic head. I'll explain to you in a few minutes that the hydraulic head is given when you have an open surface of water, is given by the water level. It's just potential energy in this case. I said that the head is a measure of energy. It can be proved that in such a situation, the potential energy is the only energy component of water, so he measured the water level on the top. You see, in this small pipe here, he measured the water level on the top. And then, what happens? He observed that there is a flow of water through the sand, so that water finally reaches the pool at the bottom. And he estimated the energy of water in the pool by just measuring the water level into the pool through, again, the small pipe on the right side. So, of course, there is a difference between the two water levels. The difference between the two water levels is difference in energy. So it's the delta H. Delta H. Here you see the infinitesimal relationship, partial derivative. If you transform and define the differences, delta H is the numerator of this ratio here. And then he estimated, he measured the length of the sand, which is the delta S. And of course he measured the flow, and he found that the velocity of the flow was directly related to the difference in height, divided by the length of the flow path. And therefore he made an experiment. And it was the experiment suggesting that it was a linear relationship. And then he concluded, okay, it's linear because the velocity is very slow. If you make the same experiment with a very coarse medium, you wouldn't find the same result. And in fact, he realized that instead of putting sand there, he tried to put gravel, and he realized that the relationship was no more valid. It was valid only for reducing velocities. So what is the hydraulic head? The hydraulic head is a measure of the energy of the flow. For a moving body, you have in general three components of energy, which are potential energy, and there is no need for me to explain what it means. There is pressure energy. Think at it. If the body is under pressure, this pressure means energy. Think of a football. If you press it, you have to put energy to press it, and if you suddenly release, the ball expands, which means that when it's pressed, it has energy. So there are, again, three components: potential energy, pressure energy, and kinetic energy. Darcy found that kinetic energy is irrelevant because velocity is very low, and therefore the hydraulic head is given by potential energy, which is given by water level, and pressure energy. If you go to the point where pressure is zero, interface between water and atmosphere, so if you measure the water level at pressure zero, you conclude that the energy, the hydraulic head, is just given by the water level, because where you measure the water level, there is zero pressure. Okay, this is Darcy's law. I explained it very briefly. I didn't go into the details. And keep in mind that there is another assumption. Fluid is incompressible. So mass density of the fluid is constant. This is, the relationship is expressed in non-steady condition because I allow dependence on time. Actually, the groundwater flow is usually evolving very slowly, and therefore, in many cases, we can assume steady-state conditions. But let's talk about now the general formulation. Okay, this is Darcy's law. And now, what is your purpose? Your purpose now is to understand the position of the freshwater-saltwater interface. So, we have this situation. Sorry, this is not working well. We have this situation. Sea level, okay, and we want to estimate the position of this interface with respect to, let's suppose that we have a bedrock here. Let's suppose that we have a bedrock here. Let's measure the position of this interface. So, keep in mind that this is an interface between salt water and fresh water. So here we must have fresh water. And the fresh water, it's limited by the water table. And typically, the water table is declining toward the sea. So I indicate in red the fresh water.
Don't we have any impermeable layers?
The bedrock is impermeable, and
Don't we have in between?
you know, if we put here an impermeable layer, we probably salt. So let's suppose that it's permeable, okay? Because of course, this is actually one of the possible interventions, that you put an impermeable layer in front of the sea. I don't know the name in English of the infrastructure that you can make if you build a wall extended in the underground. In Italian it's called taglione, which means something that cuts the ground with an impermeable layer.
Okay. What is it for? Is that to avoid the
Yes.
windshield?
Yeah. And it is the same kind of intervention when you have a river and you have a levee. When you have a levee, you want to prevent infiltration of water from the river to the land because it can siphon the levee. And then you put a wall here, which can be built also on the spot, meaning that you go there and you take the ground off and you put concrete inside. And this is called in Italian taglione, and I don't know the word in English. Do you know it?
Maybe retaining wall, but
Retaining wall. I
don't think
It's like a sheet pipe.
Sorry?
Sheet pipe.
Sheet.
Pipe.
So it is written sheet. I didn't understand. Can you please spell? Can you please spell the other word?
That's
Sheet.
pipe.
P-O-I-P-I-N-E.
P-I-L-E.
Sheet oil.
No, P-I-L-E.
Okay. Okay. P. Okay. Sheet pile. Just 1 second. I tell you. I think it may be correct. It's concrete. Yeah, it can be concrete. It can be clay. No, it can be also not clay, limestone. Sorry, it can be limestone or just 1 second. Yeah, it's sheet pile, correct. And it can be concrete, it can be, let me show you. Because I think it is an interesting finish. Sorry. Because there were some nice images, so. Okay, you see, this is one possibility, and this is not made by concrete. It is a metal layer, and sorry, my technical English for this is, you see, you put these pieces of metal, one close to the other, and they join, and then you create a sheet pile in this way. Sorry. And then there is also other examples are like this one, and they can be also made by concrete with. This is nice sheet piling. You see, with this may be an application on the coast actually. I'm not sure, but.
So what is the purpose of this shape of the sheet pile actually? Why is it not straight? You know? Is it normal?
Because because you need to join elements one with the other, and also I think there is a structural reason, meaning that it is a sheet, it's difficult to manage, and it's difficult to join. Instead, if you have elements with a shape, they are self-standing basically, and self-resistant. And because you know they need to resist the water pressure. The water pressure is much relevant, so you need a structure. A sheet wouldn't be resistant.
So the shape like this allows to decrease the pressure in every.
Yeah.
are more stiff.
Yeah, they are very stiff. Okay, and but also they make it with concrete. Here it is very often used, and also sometimes they just replace the permeable medium with an impermeable medium, like, just 1 second because I don't remember the translation. I always make confusion with the translations of, just 1 second. I think it is clay. Clay is argilla, it's argilla, correct? Yeah, with clay. Sometimes they use clay, they basically dig like a plane, and to be plane, just liquid, I'm sorry, I don't remember the term in English, and they put clay into they did like a wall, and they put clay. And this is done for BDs, but also can be done to limit saltwater intrusion. Okay, let me move forward because otherwise we won't finish here. Now let's suppose that we have here the flow of fresh water, and let's assume that the interface occurs with no mixing. Yeah, please, no problem. No mixing, which is of course a strong assumption, but it makes it reasonable to understand qualitatively how it works. And keep in mind that Darcy's law, the reason why I introduced it, is that groundwater models are essential to describe the shape of the water table. They are essential to describe the dynamics of the aquifer. And you may not need Darcy's law if you have measurements of the water table level, but sometimes you don't have measurements, or the measurements are sparse, and therefore you need to integrate the measurements with the groundwater model, and the groundwater model is based on Darcy's law. This is why I introduced Darcy's law. Okay, now, what happens at the interface? I have a picture to show you, but let me first introduce it on the blackboard, okay, because I think it is simpler. So, my purpose is to estimate, for instance, the position of the interface here. And I'm interested in determining the position of the whole interface, but let me focus on a single fluid particle that is located at the interface. Basically, this fluid particle, if it is placed on the interface, it means that it's in equilibrium. It receives, this fluid particle, a pressure from above, from the weight of the fresh water above it, and it also receives a pressure